Hello, I am Chenyi Kuang, and I'm here to present my paper, AU-Aware Dynamic 3D Face Reconstruction from Videos with Transformer. As we know, 3D face reconstruction from monocular images is a popular research area in computer vision, and using 3D deformable model for reconstructing faces is actually a well-established problem that utilizes a linear representation to approximate 3D faces, including a mean face, linear combination of shape bases, and the linear combination of the expression bases. However, there are still several challenges exists in this area. First, there is a big limit which exists in the 3D deformable model representation ability, which is hard to recover subtle facial motions. And also, training models for reconstructing 3D faces are suffering from lacking of 3D training data and labels. In addition, applying such models directly to dynamic 3D face reconstruction in videos may generate unstable and inaccurate results. Based on these challenges, we are motivated to make several improvements, including refining the expression details with spatial correlations and utilizing AU labels, which will be introduced in the next page. And also, we want to learn expression dynamics. So, why we want to build an AU-aware model for 3D face reconstruction? First, facial action unit is anatomically defined, which are directly driven by facial muscle movements, and the AUs actually represent local facial motions, which can be spatially correlated. In addition, the AU changes smoothly over time, and AU dynamics are actually exist because they are controlled by muscle contraction and or relief underlying the skin. So we made several contributions in this paper. First, we are actually the first work to present an AU-aware dynamic 3D face reconstruction framework, and we propose to model the spatial and temporal correlations of facial motions with transformer. In terms of the experiments, our model successfully achieves better 3D expression capturing and better AU recognition accuracy. So let's take an overview of our model. As shown in this image, we perform a coarse-to-fine process to generate the dynamic 3D reconstruction. It starts with a frame-by-frame reconstruction, which are noted at the coarse stage that generate a coarse sequence of 3D meshes, as shown in this gray block. And for the blue and pink block shown in this image, they are used to extract the features for both video appearance and the mesh feature. Then there are two models, which are the orange blocks, that are used to generate the AU-aware dynamic 3D face reconstruction. So it includes a temporal model and an AU spatial correlation model, and we will introduce them one by one in the following slides. For the feature extraction, we first feed the image feature to a video swing transformer that generates video appearance features. And in the meantime, we apply a pre-reconstruction to generate the 3D mesh sequences and extract the expression displacement to generate the coarse expression embedding. The video appearance feature and the 3D expression feature are concatenated as the final feature that will be used in the following stage. With the extracted feature, we first build a temporal model that models the motion dynamics. This is achieved by an autoregressive transformer, which utilizes historical AU occurrences to predict the next AUs. So we first generate the AU label embedding added with a periodic positional encoding. This is actually the input of the transformer decoder layer. And then we first apply self-attention on the AU embeddings, and then apply cross-attention among the AU embedding and the extracted feature from last slide. Then the fused feature are fed to the feed-forward network to generate the output, which are denoted as temporal embedding. The temporal model are followed by an AU spatial correlation model. As we know, according to the anatomy, the different AU pairs may be positively or negatively correlated, as shown in the two examples in this slide. And the correlation are actually reflected in geometry in terms of overlapping vertex displacement. So we propose to build an AU spatial correlation transformer to refine the 3D expression using the correlation of AUs. So we first generate expression-based AU tokens by applying element-wise multiplication between the pre-generated AU mask M and the mesh displacement. And with the AU tokens, we feed them to the transformer encoder layer to apply self-attention among the AU tokens, and then they are fed to the feed-forward network to generate the output, which is the spatial embedding. So in the final refinement stage, we combine the temporal embedding and spatial embedding that generated from the two models by adding them together and feed it to a motion decoder. The motion decoder maps the combined embedding to mesh vertex space added with the subject neutral phase to generate the final refined 3D phase for every frame. We propose different loss terms to train the full model. So the photometric loss is to compute the appearance difference between the rendered image and the original image. The landmark loss is to compute the error between the projected landmarks and the detected landmarks. We also introduce a temporal smoothness loss for the temporal embedding, which constrains the continuity between the temporal embedding for every two consecutive frames. Last but not least, there is a 3D AU classification loss, which is a binary cross-entropy loss for AU classification. Before we introduce the experimental results, we first introduce the evaluation protocol. Due to lack of ground truth 3D sequence data, we mainly evaluate the F1 score for AU classification performances to validate that our 3D physics is actually a AU-aware result. We compare with 3 types of models, including appearance-based AU recognition models and those 3D AU recognition models from the generated meshes. And there is also a most recently published work that combines appearance feature and the 3D mesh feature to perform AU recognition. For the secondary evaluation, we compared the reconstruction error with several 3D reconstruction models on a small subset of existing datasets to evaluate the mean square error and the standard deviation. In this slide, we show the AU recognition accuracy in terms of F1 score on 2 datasets, which are within dataset evaluations. So as shown in these 2 tables, our model can achieve better F1 score on both of the 2 datasets compared with most of the existing state-of-the-art models. And specifically for some AUs, our model achieves significant improvements. In this page, we also show an evaluation on the dynamic 3D faces. So we evaluate the accuracy of 3D reconstructed faces on a recently published dataset, multi-phase, and we evaluate on a small dataset, small subset. So we reconstruct the image sequence and then compare with the ground truth match sequence. And there are 2 examples shows the difference between the reconstructed faces and the ground truth faces using different methods. So in the right table, we show a comparison with 2 existing models that are using the same mesh topology with us, and it shows that on the subset of the multi-phase, our model can achieve smaller mean square error and the significant smaller standard deviation, which also indicates the smoothness. In this page, we show a visualization that compare the reconstruction quality of using different reconstruction models. And from the last row of our results, we show that our model can actually capture subtle facial motions. And more visualizations can be found in our paper. Thank you.